Lecturer Joe back again. Let's take a look at what the effect is of driving a three-phase motor from a three-phase supply where the supply is not sinusoidal. In other words, where the supply has harmonics present. Here's a look inside a squirrel cage induction motor, a three-phase motor. And you can see on the left here where the red, yellow and blue phases enter in. And these phases end up supplying a current to this stator winding. So there are basically three coils of wire here. It's not very obvious that there are three as you look at it here because they're sort of wound over one another in a strange pattern, but this basically amounts to three coils of wire. And when the three phase is supplied into this, it creates a magnetic field here which rotates. What you have is this. If you take this as being the stator, you've got your three coils, and the upshot of that is that we get a magnetic field that rotates around. We have something like this, a north and a south, single magnetic field that rotates around. In this case we're looking at it rotating clockwise because we're assuming that the three phases peak in the order red, yellow, blue, red, yellow, blue. So this is the sort of three phase that we're looking at. I've just gone with the old colours here so that you can distinguish them on the video. Red, yellow, blue, red, yellow, blue. Our voltages peak in turn one after another, and the important thing here is the sequence. So there are two possible sequences: red, yellow, blue, red, yellow, blue, or red, blue, yellow, red, blue, yellow, red, blue, yellow. This particular sequence, as you can see, is red, yellow, blue. And if we go back to our drawing, we can see that a voltage, a three-phase voltage that peaks in that sequence, red, yellow, blue, will give us a clockwise rotation. And you guys know that you can reverse the direction of a three-phase motor by switching over any two phases, because that will give you the opposite phase rotation. But here, red, yellow, blue, clockwise, because we're feeding it with this supply, red, yellow, blue, red, yellow, blue. So this is a graph I've drawn up on a spreadsheet, and we're looking here at the fundamental, the 50 Hertz three-phase. Let's take a look also then at the fifth harmonic, which is 250 Hertz. Now, as we said before, it's a much smaller voltage, as you can see from the height of the waveform here. Don't worry about this scale here, we've just scaled everything 0 to 1. So your fundamental and your fifth harmonic. Your fifth harmonic is a much smaller amplitude but a much higher frequency. You can see many more cycles here in the same time span. But there's another very important difference. If we look here at the fundamental, the sequence is red, yellow, blue, red, yellow, blue. And remember, that's driving our motor in a clockwise direction. But if we look at the fifth harmonic, the sequence is red, blue, yellow, red, blue, yellow. This is a strange outcome. What this means is that the fundamental 50 Hertz frequency is driving our motor, let's say at 1500 RPM, in a clockwise direction. But this fifth harmonic, at 5 times the frequency, because it has the opposite phase rotation, red, blue, yellow instead of red, yellow, blue, it's actually trying to drive our motor at 5 times the speed. So instead of 1500 RPM, 7500 RPM, but it's trying to drive the motor in the reverse direction. So the fifth harmonic here, if it's present in your supply, is actually trying to spin your motor backwards. Now it doesn't succeed, of course, because the voltage is much lower, but the effect of it is to cause the motor to overheat. So fundamental is driving it forward. We know that from the phase rotation red, yellow, blue, red, yellow, blue. The fifth harmonic is seeking to drive it backwards. Now I skipped over the third there because it's even more bizarre. If we plot the third harmonic, what we find is that all three phases coincide. So on our third harmonic, it may look as if we're looking at a single frequency here, but if we zoom in on this, you can actually just about see here that red, yellow and blue are actually on top of one another. So this third harmonic at 150 Hertz has the effect of producing a stationary magnetic field. It's attempting to hold the motor still. So we have this bizarre situation where if we look at the fundamental for 50 Hertz, it's trying to drive the motor forward at its regular speed, let's say 1500 RPM. The third harmonic, 3 times the frequency, if it's present in the supply, is trying to hold the motor stationary. And the fifth harmonic, if it's present, is trying to spin the motor backwards at 5 times its normal speed. And this sequence continues on up the harmonics. The seventh will be trying to drive it forward at 7 times the speed. The ninth will be trying to hold it still, and the 11th will be trying to drive it backwards. So if we had a supply voltage like this, now this is only single phase, but imagine that we have all 3 phases that look this strange shape. If we have a supply voltage like this and we're driving a 3-phase motor, the upshot is that a voltage like this is composed of a number of different frequencies, and those higher level frequencies, those harmonics, have the effect of trying to drive the motor either stationary or in the reverse direction. Now in practice, the motor spins as you expect it to in the normal direction, because the fundamental 50 Hertz is a much greater voltage than the other components. As you can see here, these are much lower voltages. But the effect is that the motor overheats. So if you're driving a 3-phase motor off a 3-phase supply which isn't sinusoidal, in other words the voltage has harmonics present, you find that the motor overheats and you're not sure why, because the motor doesn't seem to be under any particular load. You can't figure out why it's overheating, and the reason is that these higher frequency components of the supply, these higher frequency harmonics that are present, because your supply isn't a sine wave, because it's more like a square wave, these cause the motor to overheat.